Hello, so today we're going to talk about the product rule, so that will be the topic of class on Monday. So we're going to introduce the product rule and its proof in this video, and at the end we'll talk about the quotient rule. So remember that we have formulas for the sum of two functions and a constant multiple of two functions, but I don't have a lot of formulas yet, we haven't seen any, for the derivative of the product of two functions that both depend on x. So, for instance, what is the derivative of f of x is equal to x squared times x cubed? So our first guess might be, I'm just going to take the product of the two derivatives separately. So when I do that, I'm going to say maybe f prime of x is equal to the derivative of x squared times the derivative of x cubed. So when I do this, I get 2x times the derivative of 3x squared. So we're going to see, is that a good guess? When we simplify this, we get 6x cubed. So now, of course, you might say, Professor Ansaldi, we know what the derivative of x squared times x cubed is by the power rule. So our second, and in this case, more accurate guess, is to simplify first. So when we simplify first, what we get is we get f of x is equal to x to the fifth power. And when we take its derivative, we get f prime of x, which is 5x to the fourth. So what we see is our first guess here, this 6x squared cubed, that was off by a lot, right? The coefficient's wrong, it should be a 5, and the power's wrong, it should be a 4 instead of a 3. So our first guess doesn't work. Our second guess is good, just because of algebra and the power rule. But what about functions like y equals e to the x times cosine of x? We can take the derivative of e to the x and cosine x separately, and we can figure those out, but we don't know how to combine e to the x and cosine of x into a single function whose derivative we know. So what we are going to use is we're going to use something called the product rule. And the product rule is going to look a little more complicated than our normal sum rule and constant multiple rule, but it's not too bad. So say I have a function p of x, which is the product f of x times g of x. Then the derivative, and let's say f and g are both differentiable. Then the derivative, p of x, is also differentiable. And p prime of x, its derivative, is going to equal the first function left alone times the derivative of the second function plus the derivative of the first function times the second function left alone. So just to see that this is reasonable, let's go back to our example of f of x equals x squared times x cubed. All right, so I'm going to call, well, I have f again, so I'll have to use some new letters, which is fine. So I'm going to call g of x, my first function, equal x squared, and h of x, my second function, is equal to x cubed. So now g prime of x is 2x, and h prime of x is 3x squared. I always like to add or arrange my functions here in this order, and the reason is if I want to combine them, what I can do is I can just make a cross like this. So it doesn't matter as long as you have the non-differentiable things and like aren't getting mixed up too much here. So I do this cross here, and because I've done this order, I have the f prime of x. That cross reminds me of multiplication, so it's x squared times 3x squared. And then times the other line of the multiplication symbol, I have a plus here, 2x times x cubed. And when I simplify this, I get 3x to the fourth plus 2x to the fourth, or 5x to the fourth. And if you remember from our power rule, that's exactly what we expected to get just doing this the more, the cleaner way without, if we rewrote it first. So mathematicians, when we prove something like this, we want to go back to the definition of the derivative. So going back to the definition of the derivative, say I have, again, P for product, P of x equals f of x times g of x. And using the definition of the derivative, I have P prime of x is equal to the limit as h goes to 0 of P of x plus h minus P of x all over h, which, when we plug in x plus h into our definition, we get f of x plus h times g of x plus h. Here I'm replacing all my x's up here with x plus h's, and then I subtract just f of x, g of x, and I divide by h. I'm going to have to start writing a little bit smaller because even though it looks like this doesn't help us too much, I'm going to use one of mathematicians' favorite tricks. Oops, how did I get back to here? So I'm going to add 0 in a fancy way. So I'm going to add and subtract the same thing twice. So I have a couple things here. So my goal is that I want to factor this later. So I'm going to add f of x plus h times g of x plus f of x. Maybe make my pen a little smaller. X plus h, g of x. I'm out of room, but f of x, g of x is my last term. And that's all over h. So in the next step, I can make this a little bit nicer. So I have limit h goes to 0. So if I look at my first two terms here, these both have an f of x plus h. So I'm basically factoring by grouping. So I can factor out that f of x plus h. And I'm left with a g of x plus h in the first term and a g of x in the second term. And then in my second bit of terms, which is again hard to see, I apologize, both of these terms, so it's f of x plus h times g of x minus f of x times g of x. So these two terms both have a g of x. So I'm going to factor out that g of x. And the first term has left an f of x plus h, and the second term just has an f of x. And this is all divided by h. I can divide this now into two separate fractions around the numerator. So my first fraction is f of x plus h times g of x plus h minus g of x, and divide by h. And I'm just going to split my limit at the same time. So I've got g of x, f of x plus h minus f of x all over h. And if we look at this, I can even move my limits even further. So I have the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x over h. And then I've got my limit. Well, the g of x doesn't even have a h in it, so I can just move it right outside the limit, so it's just g of x. and then the limit as h goes to 0 of f of x plus h minus f of x. Again, I'm at the edge of that screen, over h. All right, so now let's look at the pieces. Okay, first limit, this red circle limit. Well, if I can just plug in f is a continuous function. And so what do I get when I plug in h equal to 0? I just get f of x. Second limit, my green limit, that is nothing but our definition of the derivative for g prime of x. And I've got a blue limit. Well, that's not even a limit, just a g of x. And my final one, hey, there's the limit definition of f prime of x. So there we have it. We've got the product rule. So what I want you to try is use the product rule to take the derivative of the function f of x equals x squared e to the x. So that will be problem number 1. All right, so that's the first part of our video. So we have a longer video today, so we can jump right into problems in class on Monday, because this is sometimes a challenging topic, so we want as much practice as we can. So the second part of our video is the quotient rule, and I'm not going to go through the proof of this. So what does the quotient rule say? Well, in this case, we're going to think about derivatives that are quotients or fractions. And the derivative formula for a fraction is f prime g minus f g prime all over g squared. So that's a little more complicated to memorize than when we did the product rule. So what we sometimes use instead, a mnemonic I've seen works for a lot of people, is we think of f over g prime. I'm really thinking about this as a high function minus over a low function prime. And then there's a nice little rhyme to memorize the quotient rule. And that is that the derivative is low, so d high. So there we go. So that's just kind of writing this first term in a different order. Minus high d low all over the square of what's below. And that's where we get that g squared. So I'll do one example. So my example is f of x equals x squared over sine of x. And so let's go through our rhyme. F prime of x is equal to low d high, so sine of x gets left alone, times the derivative of the numerator, which is 2x, minus high d low, x squared, times the derivative of sine, which we saw was cosine. And then I'm dividing everything by sine of x squared. And because we're not doing anything else with this, I'm just going to leave this exactly like this. What I would like you to do is I would like you to differentiate the function f of x equals e to the x over x. And that will be question number 2. So I will leave you with those questions. We will practice this a lot more come Monday in class, and we'll use this to do all kinds of exciting new derivatives.